Myself, Murali Krishna, Assistant Professor, P.V. Raju Institute of Technology, Narsapur, Department of Physics. Today, I am going to discuss numerical aperture and types of optical fiber. And in earlier class, we discussed about the acceptance angle. Now, we are going to discuss the numerical aperture. The numerical aperture is the light collecting ability of the optical fiber. It is depend upon the acceptance angle. The numerical aperture is the sign of acceptance angle. The numerical aperture NA equal to sin I maximum equal to root over n1 square minus n2 square. N1 is the refractive index of core material, N2 is the refractive index of cladding material. Now, we are going to discuss about the types of the optical fiber. Optical fibers are classified on three categories based on the material, based on the modes, based on the refractive index profile, and based on the material. What type of material is used to fabricate the core and cladding in an optical fiber? That is called a glass optical fiber and plastic optical fiber. In a glass optical fiber, silica is doped with some impurities. Pure silica is a core material and doped with some impurity is a cladding material. And a plastic optical fiber is a transparent plastic is used to fabricate the core and cladding material. And mode of transmission. The mode of transmission is nothing but it is depend upon the diameter of the core material. Single mode or multi mode. Based on the modes of transmission, the optical fibers are classified into two types. One is the single mode optical fiber and multi-mode optical fiber. Now, this is the optical fiber. Only one wave can transmit through the optical fiber, that is called single mode optical fiber. Suppose this is the optical fiber core material. More than two rays, more than two waves can transmit through the optical fiber. That is called the multi-mode optical fiber. And third one is third classification is the step index fiber and gradient index fiber. This is the step index fiber and this is the gradient index fiber. Here, the entire core material made up with unique material. That's the reason its refractive index is a unique entire core. But in a gradient index fiber, the refractive index of core material radially varies. That means at the center of the core is a maximum. The center of core is a maximum refractive index, and away from the center, the refractive index gradually decreases. And this is called a gradient index optical fiber. This is the cross-section view of the step index optical fiber and gradient index optical fiber. This is the inner part is core material, entire core material made up with single material. It has a refractive index is a unique, and cladding is abrupt change at a core clad interface. The cladding refractive index is different N2. Now here the core refractive index at a middle is refractive index is very high. When away from the center, refractive index gradually decreases. Now, this is the inner structure of the gradient refractive index. The core material is made up with several material. It has several layers, and this is the inner layer. The refractive index of inner layer is NA. And this inner layer is surrounded by another layer and another layer, and this refractive index of inner layer is NA, and refractive index of outer layer NB, NC, ND, and so on. The condition is NA greater than NB greater than NC greater than so on. That means inner core is a denser medium. You are away from the center of the core. The layers refractive index gradually decreases. And this is the comparison between the step index and grad index optical fiber. The refractive index of core is uniform throughout and undergoes abrupt change at a core cladding boundary. The refractive index and grad index optical fiber, the refractive index of core is made to vary gradually such that it is maximum at the center of the core and center of the core. The diameter of the core is 50 to 200 micrometer in case of a multi-mode fiber and 10 micrometer in case of a single mode fiber. In a grad index fiber, the diameter of the core is about 50 micrometer in case of multi-mode fiber. The path of light propagation in a step index fiber in a zigzag form and grad index fiber in a helical manner. That means this is the optical fiber. The light ray can transmit in form of a helical manner in a step index fiber in a zigzag manner. And attenuation is more in a step index fiber. Attenuation is less in a grad index fiber. When the light ray travels through the optical fiber and attenuation is formed. Optical fiber, when a ray travels through a longer distance, there will be some difference in a reflected angles. Hence, higher angles rays arrive later than the lower angle rays, causing the dispersion, resulting in a distorted output. The attenuation is less in a grad index optical fiber. Here, the light rays travel with different velocity in different paths because of the variation in their refractive indices. At the outer edge, it travels faster than near the center, but almost all rays exist at the same time due to the helical path. Thus, there is no dispersion. And the fiber has a lower bandwidth and the grad index fiber has a higher bandwidth. That's the reason grad index fibers are used for the long distance communication system. The step index fiber, the light ray propagates in the form of a meridional rays. It passes through the fiber axis. The light propagation in the form of a skew rays and it is not cross the fiber axis. Number of modes. How many modes can transmit? How many signals can transmit through the step index multi-mode fiber? That is n step equal to 4.9 into d into numerical aperture by lambda whole square equal to v square by 2. V is one constant where d equal to n step number of modes can propagate through the optical fiber. This is the formula. And D is the diameter of the core and NA numerical aperture of the optical fiber and lambda is the wavelength of light we transmit through the optical fiber. V number, suppose its value is 2.40 per 405 per single mode and 2.40 greater than 2.405 per multi-mode optical fiber. Number of modes propagation through the n graded, that is 4.9 into d into numerical aperture by lambda whole square by 2. That means square by 4. Finally, number of graded equal to n step by 2. Finally, I conclude that the grad index fiber transmit less number of modes compared to the step index optical fiber, but the signal loss is very less. Now, when a light transmits through the optical fiber, some signal loss can occur. Now, that is called the attenuation in an optical fiber. Attenuation. The signal loss of optical power during the transmission through an optical fiber is known as a attenuation. It is denoted by alpha. When a light propagates through the optical fiber, some amount of optical power loss occurred through occurred through some mechanisms. That is alpha equal attenuation alpha equal to minus 10 by L log base 10 P output by P input, where L is the length of the optical fiber, P output by P input. Suppose this is one optical fiber. This is the first end. This is the P in. What is the P out? Now this is the total length of the optical fiber. Now the attenuation can be measured in attenuation alpha equal to minus 10 by L log base 10 P output by P input. Now, what is the optical power launched into the optical fiber? What is the optical power received at the receiver end? That is called P output. Now, due to the attenuation occurred in optical fiber due to these mechanisms: absorption losses, scattering losses, and bending losses. This is the graph: wavelength on x-axis, decibel per kilometer on y-axis. Absorption loss. The absorption loss is a wavelength dependent loss. Now, where the at a lower wavelength below 700 nanometer wavelength, the absorption loss is very high. When the wavelength of light launched into the optical fiber increases, the absorption loss is decreasing. And finally, it is reached to very lower value. And whenever the wavelength of light is at a 980 nanometer, again it is increasing, and again it decreases drastically. Again 1250 again increases. And suppose OH ions present in the optical fiber, the OH ions absorbs more light at 1380 nanometer. This is called absorption loss. And the scattering loss. The scattering loss generally it is also wavelength dependent loss. The Rayleigh scattering loss is proportional to 1 by lambda power 4. That means the wavelength increases. The scattering loss also decreases. Scattering loss decreases. Now it is purely depend upon the wavelength. Generally, the scattering losses occur due to the imperfection crystal of the core material. This is the core material. In this core material, suppose the atoms are not arranged in a regular form, or a imperfect crystal, or at a high density clusters are formed in some regions. Whenever the light transmit through such type of high density clusters, this light ray scatters in all direction. Due to this, signal strength will come down, and this is called a Rayleigh scattering. The scattering loss occurred due to the imperfection of the crystal. This is also wavelength dependent loss. When lower wavelength, the loss is very high. Wavelength increases, the loss is decreasing. And next one is the bending loss. There are two types of bendings are there: microscopic bending and macroscopic bending. Microscopic bending. This is the optical fiber. This is the inner core. This is the core material. The microscopic loss are caused by the small discontinuities or imperfection in the fiber. Okay, uneven coating application and improper cabling process increases micro bend loss. And suppose here the optical fiber just slightly bends. Whenever the light ray enters into the curved surface, it does not satisfy the condition for a total internal reflection. This angle of incident is less than the critical angle. This light ray can escape from the core material. Now, due to this, some signal can enter into the cladding material. Now, macroscopic bend. Suppose this is the optical fiber bends more at this area curvature is more. Whenever the light ray incident on the bends area, now the angle of incident is less than the angle of incident is less than the critical angle. The angle of incident I less than the critical angle at a core clad interface. Now the light ray can escape from the core material. This is called the macroscopic bending losses. And these are the important attenuation in a optical fiber. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.